generator, the generator that generates the alternating current. In an alternating current circuit, we use this symbol in place of the battery that we have seen earlier. Alright, let's now talk about the alternating current in a resistor. Well, we know about direct current in a resistor, controlled by Ohm's law. Is that right? The potential difference V equal to IR. Is that valid for alternating current? Well, I have here a circuit. This is the generator connected to a resistor R. When we apply an AC voltage to a resistor, the current will flow through the resistor. But remember that current will be varying and alternating. Can we apply Ohm's law as we did with the DC? Well, how can we even specify the AC voltage since it is constantly changing? Therefore, before we talk about this, we need to talk about how we deal with such a changing voltage. An AC voltage never remains steady. So, let's first of all talk about the RMS value of an AC. The RMS value is something that is familiar to you, root mean square. A quantity that is continuously changing and reversing in direction. If you take the average value over a period of time, it will be 0. And therefore, to deal with it, we talk about the root mean square. If you remember how we obtained the root mean square velocities of moving molecules. It's the same concept here. When you have a value varying sinusoidally, the average value will be 0 because half the time the values are positive and the other half the values are negative. One way to deal with this is to describe what we call the RMS value. What does RMS value stand for? It stands for root mean square. In other words, we take the square root of the average of the squares of all the current or EMF. That is the root mean square. To calculate the RMS value of an alternating current, we first square all the I values to make sure that they are all positive. Then we take the average of all that, and once you find the average of all the I squared values, then we take the square root. That is what we call the root mean square value. So IRMS, the root mean square value of the current, is square root of the average of all the I squared. And that will be, the instantaneous value is I0 sine omega t. So square root of I squared sine omega t squared. And this can be shown to be equal to I max divided by square root of 2. Now, what I want you to do is to recognize the relation between IRMS and I max. The RMS value of the current is related to the maximum current as IRMS equal to I max divided by square root 2. In the same way, the EMF is also related as ERMS equal to E max divided by, so VRMS, or the RMS value of the voltage, is V max, the maximum value of the voltage, divided by square root of 2. We will use these very often. That means I max equal to IRMS times square root 2, and V max is VRMS divided by square root of 2. Well, when we talk about the 110 voltage AC that we use at home, is that the RMS value or the peak value or the maximum value? Well, of course it is the RMS value and not the peak value. Now, in a resistor, the voltage and current are in phase. What does that mean? The voltage and current are in phase. It means when the voltage increases, the current also increases along with it, and when the voltage is a maximum, the current is a maximum, and so on. They are in phase. Now you can see here, as the voltage increases, the current also increases. The voltage is 0, the current is 0, so the voltage and the current are in phase. Now we can use Ohm's law to establish a relation between voltage and current. Yes, when an AC passes through a resistor, we can use Ohm's law, and that will give us a relation between Vrms and Irms, as Vrms equal to Irms times R, or Irms equal to Vrms divided by R. How about the average power? The average power will be always positive. Is that right? Because the average power is Erms multiplied by Irms. Because E and I are in phase, when E is negative, I also is negative, so the product will be positive. So although I can be positive and I can be positive or negative, E also can be positive or negative, but the product, the power, will always be positive. Now, circuits in which current is proportional to voltage are called linear circuits. In a resistor, the current is proportional to the voltage, therefore it is a linear circuit. Now, the ratio of voltage to current in a resistor we call resistance. Is that right? Resistance is the ratio of voltage to current. Now, in the case of a resistor, the resistance does not depend on the frequency. In other words, the resistance of a conductor does not depend on how fast the coil rotates to generate that AC. It is independent of the frequency. Now, but this is not true when you consider AC that passes through a capacitor or an inductor. What is an inductor? We talked about it in the last class. Well, we will be looking at that in detail in this lesson. Now, in an alternating current circuits that contain capacitors and inductors, the ratio of voltage to current does depend on the frequency. I want you to understand this very well. For a resistor, the resistance does not depend on the ratio of voltage to current. But when an alternating current passes through a capacitor or an inductor, the ratio of voltage to current depends on the frequency of the AC. That's a big difference there. In general, in an AC circuit, there is a phase difference between voltage and current. Now, in the case of a resistor, voltage and current are in phase. And so, the ratio of voltage to current is the resistance. But in the case of a capacitor or an inductor, the voltage and current are not in phase. So we can say, in general, in an AC circuit, there is a phase difference between voltage and current. The only exception is the resistance, where they are in phase. Now, in such a case, the ratio of voltage to current is called the impedance of the circuit, and we represent that by Z. So, in the case where there is a phase difference between voltage and current, you will not call the quantity, the ratio of voltage to current, resistance, but we call it impedance. In fact, resistance is a special case of impedance. In the case where the voltage and current are out of phase by 90 degrees, this is a particular case again. Now, there are two particular cases we are discussing. where the phase difference is 0, that impedance is called the resistance, and that is the case of the resistor. If the phase difference is 90 degrees, that means the voltage and current are out of phase by 90 degrees, then that impedance is called the reactance. The reactance, and will be represented by uppercase X. The reactance of a capacitor will be written as X sub C, and the reactance of an inductor will be written X sub L. If you remember, we used L for inductance of a coil. And it is measured in the same unit as resistance, namely ohms. Alright, let's do an example. A 12 ohm resistor is connected across an alternating EMF that has a peak value of 48 volts. So this is the maximum voltage. Find the RMS current, the average power, and the maximum power. It's a very simple direct application. You know that Vmax is given to be 48 volts, and we need to find the Vrms, we need to find the RMS current. If you want to find the RMS current, we need the RMS voltage. Vrms is Vmax divided by square root of 2. And that will be 48 volts divided by square root 2, that is 33.9 volts. Once you know the value of Vrms, then Irms is Vrms divided by the resistance which is given, and so that will be 2.83 ampere. We need to find the average power. The average power is the product of Vrms and Irms, and we know both these values, and that gives you the average power as 96 watt. What is the maximum power? The maximum power will be the product of Vmax and Imax. And in order to find Imax, well, Imax is square root 2 times Irms, and that will be 4 ampere. Therefore, maximum power is Vmax times Imax, that is 192 watts. Alright, let's now talk about